Hi folks, as I promised about almost a week and a half ago by now, today I want to tell you a couple things I've done on the hardware random number generator project. And more specifically today I want to talk about the firmware I've written for the microcontroller. And what has happened there. No, despite the t-shirt, I'm not going to talk about IPv6 today, and I'm not going to try and use a 32-bit microcontroller for the job either. It's just that it was, well, still reasonably okay to wear, so I just grabbed it. Well, whatever. Okay, so what about the firmware thing on this project? I actually had to take notes so I don't lose track at some point. First decision I had to make was what sort of output I wanted to deliver at the USB interface of this entire contraption. And there are basically two options there. One is to provide as much low entropy noise sort of stuff, feed that through some sort of mechanism to the, for example, Linux kernel, and let it use that low entropy stuff to reseed its pseudo-random or crypto pseudo-random number generator. And the other option is to make sure that whatever comes out of this device is actually high quality random data. And I decided for the latter. Why is that? Well, first off, where's the challenge otherwise? But more importantly, with the current setup, with the FTDI serial to USB interface, I can only get about 500 kilobits, or I can get 500 kilobits per second of gross data from the ATtiny to the serial interface, or through the serial interface to the PC. And if I use an 8N1 encoding, one start bit, 8 data bits, one stop bit, no parity, that means I get a net throughput of 50 kilobytes per second maximum, theoretical maximum. In fact, I'm currently at about 20 kilobits per second, and I'm not yet sure if that really works. More about that some later time. And I think that makes pretty good use of the resources I have there. If I was just trying to deliver as much noise as I could, the bottleneck would actually be the serial interface there. So that was the first decision I've made. And then there's one of those things you want to do when you deal with algorithms and computers and that sort of stuff, which is a very good habit, which is just playing with the numbers a little bit. The Atmel microcontrollers can run at up to 20 megahertz per second, which I'm currently using. I generate 20 kilobytes per second of output. So that means I have about 1,000 clock cycles per byte of random data I generate, or 125 clock cycles per bit, which isn't all that much. Especially so because you need more noise than a single bit or a single measurement from the input pin here to get some serious high quality random noise. And that said, it already means there is one decision fairly obvious at that point, and that is I'm not going to use interrupts at this point. Because even on the Atmel microcontrollers, which are pretty good at that, they don't have to do proper context switches and nothing, but still they need 4 clock cycles just to start an interrupt handler. And then they have to push registers out of the way, and afterwards they have to pop registers back again, and then have to return to wherever the interrupt actually hit the main program. And that's getting prohibitively expensive quite quickly. Aside from that, interrupts always mess up with timing related stuff, so it's not really the first choice to use, despite the fact that all real kernel hacker sort of people do interrupt stuff because it's cool and tricky and shows how what experts they are and whatever. Just forget about that. I want to get something done and not to show off. Okay, so that's the situation here. And one more thing about hooking up the analog noise generator to the microcontroller. I'm not going through the analog input, the ADC, the analog digital converter, because converting some analog input into some digital data is simply too slow on these microcontrollers. It doesn't make sense. So all I do is I connect the generator to a digital input pin and read zeros and ones out of there. Good enough for the job anyway. So how's this stuff programmed? Well, oh, by the way, I'm not going to give you a full walkthrough of the code and show you on the computer, because I decided if I do it properly and explain everything I'm doing there, I'll drive away anybody who already knows about microcontroller programming. And if I skip the stuff that's specific to microcontrollers or Atmel microcontrollers in particular, I drive everybody else away who doesn't know about these things in detail. So I decided, no, it's just boring. It doesn't make much fun. It doesn't make much sense. So I'm not going to do that. Instead, I'll tell you a couple things that I've done so you get an idea how this all fits together. And as soon as this stuff gets sort of stable and the PCB is finalized, I'll put things online and you can take a look at the sources. They're getting better, but I've spent about a week rewriting the stuff because what I've used so far was really for my personal testing. It was beyond redemption. It was simply no way to make that useful or readable or understandable to anybody else. And that way for that reason I decided I'd do it from scratch. Was okay. Took me a couple of days, a couple of evenings basically. But okay. Now there are two fundamental components you even know from your favorite Arduino projects. If you do that sort of stuff, you pretty much always need some sort of initialization code, which is only run once when the microcontroller powers up. And then there's a main loop which is run and rerun and rerun, well, until there's no power any longer. So yeah, I've done the same, and that works perfectly well. Not much of a surprise. However, then I've done something to make this configurable, because I don't really know what sort of algorithms work best for the job. So I made this entire thing configurable. Basically, I've got a makefile, and in that makefile I include another makefile which I use to store some sort of configuration stuff in there. And by directing the main makefile to include whatever profile makefile, that's what I call them, I can build different firmwares for the microcontroller with different properties and can test things out, because that's what I'm currently doing. Okay, so that's how it works, and there are several subsystems. Big fancy work for a couple lines of code, but yeah, I've got a degree in computer science. I have to do these things that way, right? Otherwise that wouldn't be good for my reputation. Aside from the fact it actually makes sense to some degree. And if you take a look at the output, it sounds like it's completely over-designed, but at least the assembly code output is rather straightforward. Okay, so first module I have is for status LEDs, because I want to see what's going on. I've got two LEDs hooked up right now. Green one means that thing is idle and waiting for the PC to get ready to receive data using hardware flow control. Red would mean it is actively generating and sending data. And what's nice about it is not only that you can see what's going on, but you can actually hook up oscilloscope to that. And if you measure duty cycles, you can actually see how the CPU on the microcontroller is actually, to what degree it is busy. Quite nice actually. And yeah, that was pretty much one of the most simple things you'd want to do. You'd always, if you start anything like that, first thing you want to do is make sure you can make an LED blink so you know your toolchain is working. At least I do it like that. And well, that's what I've started with. Second thing I've done was to come up with an I/O subsystem. And actually there are a couple possible I/O subsystems. I could do SPI, I could do I2C, but the only one I've done so far is the serial interface, because I'm currently using the FTDI chip anyway. And no big surprises there. Flow control was effectively one line of C code. Basically, the routine that actually writes out data has to wait for the RTS pin on the FTDI chip to go low. And two more lines in the makefile to tell where the RTS pin from the FTDI chip is actually connected to the microcontroller. Rocket science, really. And I got that to work. And next thing I wanted to do was test that. So I didn't do anything about reading from the noise generator or so, but what I did was write a simple ripple generator, like those ripple generator things you'd have on those old dot matrix printers, where they print a repetitive pattern of characters so you could check that your printing head was okay and whatnot. Just the same thing. Good news is with that I could test that the hardware flow control is working. And of course I have something to test the FTDI chip with. Now I'll have to write a couple more things like that and some more advanced stuff. But what that means is if I run that sort of firmware on the microcontroller through the FTDI chip and then check the output at the computer, I can kind of make sure that nobody added some security features, functionalities to the FTDI chip. So I can actually do some sort of auditing of the FTDI chip, which is especially important because I can't look inside. I can't even really look underneath once it's soldered onto the PCB. So I want to make that reasonably sure. And yeah, works nice. So at that point I could actually go and do something about random data. Well, the first decision at that point I had to make was, do I want to have a single such noise generator and just use the output serially, basically collect 8 bits of random data, put them in a byte and then send them off to the serial interface or whatever I/O subsystem? Or do I want to have maybe 8 of these in parallel and use them in parallel? For now I decided to go for a serial setup. Why? Less hardware. So it's easier to build, easier to build, cheaper to build. It's much easier to audit. If you have 8 of these noise generators, you'd have to audit all 8 of them. This way you just have to audit one. And finally, some of the mechanisms that I'm using are not very well suited for parallelization. So I read out bits one at a time from whatever I do to make the noise I get from this device into proper random bits, push them in a byte and then send that out. Well, actually I've made a bit of an option that I read more than 8 bits to kind of flush the system. So in case there is some sort of interference between the serial interface and the microcontroller, maybe because of some voltage changes or whatever, then I could actually compensate for that. So far I don't have any indication that this is necessary, but tests are still underway. So we'll see about that. Next problem is, how do I turn bits of noise into bits of random data? And that sounds fairly trivial, just take the bits of noise and put them in there, but it actually isn't. Why is that? The noise generator, as we've seen on the oscilloscope in one of the previous episodes, is fairly equally biased, roughly, but roughly isn't good enough. We want things to be really equally distributed zeros and ones. And just reading some random, some sort of noise from the device directly doesn't make that much sense. Why? There's component tolerances, of course. There are aging effects on components, and considering there is currently quite an ugly heat wave going through Germany, things might actually be, for example, temperature dependent. So I'm not going to assume that the noise I get from the noise generator is actually unbiased. What can I do about that then? Well, I could use it as is, and I might try to sort that out when actually reading the individual bits. But there's a better way to do this, which is called a von Neumann extractor, after John von Neumann, which basically works like this. I have some sort of random noise input which may be biased. That's okay. It'll make things slow down, because if it's biased, it'll contain less entropy or information content. And that means there's less randomness I can extract from it. Well, if there is no entropy, I can't extract any. How does a von Neumann extractor work? Well, I take 2 bits of input. If they are the same, I throw them away. But if they are different, so if I have a 0, 1 or 1, 0, well, I use 1 to indicate 0 and the other one to indicate 1, and then return that as output. Problem there is, on average, even if the input is unbiased, I need on average 4 bits of biased noise to generate 1 bit of actual unbiased output. But okay. Also means if I do that in the microcontroller rather than on the PC eventually, then I need 1/4 the bandwidth through the serial interface. Makes sense for now. However, there are a couple things in the fine print with von Neumann extractors which deserve a bit of attention. First off, and you don't find that in Wikipedia, if the bias of the noise source is changing, then that may lead to a bias of the output of the von Neumann generator. I've got no clue if this is a serious problem. I'll have to check, basically, writing some more test code and see how that works out. But that might at least theoretically be a problem. There are ways to minimize that effect, chewing up more bits, but right now I guess I won't need them. It's just good to know that there are ways to do that. The other one has to do, and this is where it's getting really ugly, that the von Neumann extractor only works if the individual noise bits are actually not correlated. They may be biased, but they must not be correlated. So from a series of inputs, I must not be able to guess some other bits beyond that, or before that, in between that, or whatever. Which is a problem. Decorrelation is a huge challenge. More on that in a moment, and in the next probably 2 episodes. But before I talk about that, there's one more question. How do I actually read the noise out of my noise generator? Now, the easiest way to do is just do a single binary read and just use that. It'll be biased, which is bad for the von Neumann extractor because it'll make the von Neumann extractor less efficient, but it works. I can actually speed things up, however, if I do multiple reads and XOR them, because that'll reduce the bias and it'll actually speed up the von Neumann extractor, possibly to a point, you have to find the proper number of XOR readings, to a point that the overall throughput will increase. However, that still has a problem. If the noise generator breaks, it flatlines, so it'll return only zeros or only ones. It doesn't matter which one. What does that mean? well, the Funmoment extractor will still return, no, sorry, the Funmoment extractor will sort that out, which is okay. But what if the entire thing kind of slows down? Then I have more correlation. That's a big problem at this point. Sorted out a couple of things with the Funmoment extractor already, but what if things slow down or speed up? But that's unlikely. The best way I've actually found to read data out of the generator is not to measure one or several levels, but to measure the time between rising edges. Rising edge basically is you read a 0 first and then a 1 afterwards, and you wait for the same thing to happen, you measure how long it takes in between. What's nice about this is that if the average frequency, if you like, of the frequency spectrum of the noise generator shifts down, that'll make the whole thing slow down in a rather, well, kind of healthy way, which is good. And it actually works quite nicely. I get some pretty good results that way. So that's what I'm currently using. Might go back to the XOR variety, but we'll see. It really boils down to taking some measurements and running tests and taking some more measurements and running some more tests, and that takes just weeks. Okay. One more question is, how do I make sure that individual bits of data that I generate are not correlated? In the previous episode I mentioned one approach that I've been playing around with, which was to kind of reset the noise generator before I ever do a reading. It works at about 1/10 of the speed I'd get otherwise. So unless it's getting really, really difficult to get some decent output otherwise, I'm just going to ignore that. It's extra hardware, so there are extra things that can fail, extra things that have to be audited, and it's just not really worth it. Second approach is to wait some sort of fixed amount of time before I actually do another measurement. Yeah, possible. Implemented it. Works quite straightforward. Just gives me a stupid compiler warning that I can easily ignore, but can't really switch off. And yeah, it's there. Another thing that is interesting, which I haven't yet implemented, is, however, to set up one of the microcontroller timers and only generate bits at fixed intervals. Almost the same effect, except that way it'll be pretty much impossible to do timing attacks on the output, because output will occur at pretty much fixed interval times. Has its bit of beauty. And the final approach, of course, is to wait for a number of rising edges again, which is what I currently favor most, because it adapts to the properties of, or some of the properties of, the noise generator. So yeah, that's pretty much it. And by the way, if you wonder why I don't just, read bits in a different order to decorrelate them, that doesn't work. Why is that? It means that the correlation is harder to detect, but it's still there. You won't get more entropy that way. So all you do is you make it more difficult to audit the entire thing. And it doesn't help. What I want to do is make this thing easy to audit, which means I have to come up with a design that has fairly obvious failure modes. Then I can figure out where there's the most likely correlations and look for them. And afterwards, maybe sort of mix them. For that job, do it properly and use the output of the hardware generator as input to a cryptographic pseudo-random number generator, like Fortuna, or maybe if you don't have anything else, Yarrow. And that's a bit counterintuitive, but that's actually fairly important. I mean, this is meant to be auditable. That's the whole reason why I built this. So we better accept this sort of thing. Okay, so that's what I've done as far as firmware goes. With the current profile, I currently get less than 30 ppm, 30 parts per million bias. Probably better, but it needs lots and lots and lots of output to test for even better results. Basically, it works like this. I say, okay, I need to make sure with the 6 sigma probability or confidence, 6 sigma is there's one error in 3.4 million, so I think pretty much 0. That the output is biased no more than, let's say, 30 ppm. And then I know, okay, I need this much test data to test, and the output should be within this window of bias. And yeah, 30 ppm at 6 sigma is already confirmed, and if I generate 100 times as much test data, I could even go down to 3 ppm. Only for 30 ppm I already need a gigabyte, and wait until this thing has provided 100 gigabytes worth of data. It's going to take months, so haven't gone there yet. Currently the output speed is about 19 kilobytes per second, which I consider pretty good. I don't have any tests for correlation yet, except that what I do is I use existing tests from other people which had their problem, which will be the topic for the next episode, and they don't find any flaws with the output so far. So that's cool. And what am I going to do next? First, more testing, especially with the correlation stuff. Then eventually decide what sort of profile I consider reasonable. Yeah, and then it's getting ugly, really ugly. I'm afraid I have to take a look at the assembly code output from the compiler, see if this is like I'd expect. And if things get really ugly, I might even decide I'm going to rewrite the entire driver or the entire firmware using assembler code. Hate it. I've learned assembler on Intel CPUs. I mean, that leaves emotional scars for the rest of your life. But, well, I have a goal, and if that's the only way to do it, well, I guess I will. Okay, so that's where I'm at so far. If you have ideas, suggestions, complaints, whatever, come over to the forum at www.stepladder-it.com/BIVBlog/28. If you like this, watch this on YouTube, do me a favor and give it a thumbs up. And in any case, hopefully see you in, well, by now, less than a week. Okay, so long, bye.